Hello, everybody. Welcome to this talk. My name is Panos Alexopoulos, and today I'm going to talk to you about the topic of robustness in natural language processing. To give you a bit of background about myself, I've been working for around 16 years now in the field of data semantics and natural language processing, both as a researcher and practitioner. And for the last 6 years, my role is in a company called Textkernel, where I lead a team that is responsible for developing and delivering a large knowledge graph about the HR and recruitment domain. And a big part of developing such a knowledge graph is using natural language processing and machine learning in order to extract domain knowledge from unstructured information and text. So today, I want to talk to you about a particular quality dimension in natural language processing that is called robustness. I think that the majority of you that are attending this event are aware that in the last 5 to 10 years, we have been witnessing a great increase in the accuracy of NLP systems for many basic and downstream tasks, especially after deep learning and the transformer architecture was introduced, with its most striking examples, BERT-based architectures, and of course lately large language models like GPT-3 or Bloom. We have seen a very important improvement in many tasks, including text generation, question answering, relation extraction, etc. However, there is a catch, if you like, in this increased accuracy, and it's the fact that it's the observation rather that in many of these sophisticated NLP systems suffer from an important problem, which is called fragility. To understand what fragility is, let's take an example of a sentiment analysis system, right? That takes as input a piece of text, usually from some review of something, and tries to determine whether this text expresses a positive or negative sentiment. So, for example, in this table, the first sentence that you can see expresses a review, an opinion about a particular Chinese film, and as you can see, the system correctly identifies that the review is positive with some level of confidence of 77%. Now, where this becomes interesting is when the input changes just by only a single character. So instead of having connoisseurs, the first C of that letter changes into an A. You can see that immediately the prediction becomes negative, which is a very counterintuitive and, of course, not desirable feature. You don't want this from your system because it doesn't seem to make sense. It's not just wrong, it's embarrassingly wrong. And the same could be said for other types of changes, like replacing the word film with the synonym footage. So if we want to give a definition to the problem of fragility, is that an NLP system is fragile when small changes in its input can produce substantially wrong output. So the problem with fragile NLP systems is that they do not generalize well across different data and can perform quite badly when you deploy them in real-world applications. So if we take fragility and we inverse it, we can say that a system's ability to be resilient to variation in data, to small variations in data, is called robustness. So the question that naturally arises is, how can we assess robustness? This is where adversarial evaluation enters the stage. If you have been developing NLP systems, you are probably aware of the fact that of the typical way we evaluate such a system. So usually we take the data that we have trained our system on, we split this data into training and test data, and after we have performed the training, we use the test data to evaluate the system's performance, usually through scores like accuracy, precision, recall, F1, etc. The problem with the limitation of this type of evaluation is that it only reveals problems and weaknesses that are expressed in the data that we have available and that follow the distribution that follow the same distribution. So if we deploy the system in a situation, in an environment where the data distribution might change, we cannot know a priori if the system will perform as it should, as predicted. Adversarial evaluation, on the other hand, starts from custom data. Instead of taking data from the same distribution as the ones that the system has been trained on, instead, we create custom data that contain particular patterns and phenomena that we care to test about. These patterns and phenomena can be, for example, negation, synonymy, typos, as we saw earlier, and generally any other nature, any other form of data that we suspect that might be given as input to our system and our training data do not necessarily reflect on. Our goal is to make the system reveal weaknesses that are not reflected in the training data. So, how can we perform an adversarial evaluation? There are practically 5 steps into this process. As a first step, we need to define the task that we want to evaluate and the target systems that we want to perform the adversarial evaluation on. Right? The task can be a basic task like part of speech tagging or next word predictions and things like that, or it can be a downstream task like natural language, relation extraction, entity extraction, question answering, sentiment analysis, etc. The second step is to specify the adversaries, to specify the adversarial patterns and phenomena that we want to test the systems on. And the way to think here is what can possibly go wrong with the system, right? Usually we have to think as hackers, that's hence my previous image that you saw. We have to think as hackers that we want to actually break the system. And we need to think what kind of phenomena most probably the system will not be able to satisfactorily tackle. The third step is to generate data that reflect these adversaries and that then can be used for to test the systems. This data can be generated manually or automatically or semi-automatically. There are actually several toolkits currently in the research community that allow you to very quickly generate such data. The fourth step would be to apply the adversarial data to the systems under evaluation and get the output. And finally, given that output, to actually measure what has been the impact of this adversarial input. Has the performance of the system stayed the same, been reduced? And if so, what types of adversaries have resulted, for example, into the lowest or highest decrease? To understand better this process, I will describe a case study where in my company we evaluated 2 state-of-the-art relation extraction models for the purpose of building our knowledge graphs. As I said earlier, relation extraction is an important task that we want to do for knowledge graphs, and it's also a task that enjoys. It's quite difficult and very prone to fragility, as we will see. So, to formally define the task involves having text and having pairs of entities that we want to identify if these entities in a given text are related through a particular relation. So, for instance, if we take the entity Beijing and China, we want to know if in this particular text this pair is related via the relation is capital of. So to be clear, the entities are a given, the relation type is a given. What we want to get as output is if in a particular text this relation is expressed or not. For this particular case study, we targeted 2 systems. Both systems are based on transformers on BERT, but they have a basic difference. So the first system, called Look, is a transformer-based system that is pre-trained on Wikipedia, and is particularly pre-trained for the relation extraction task. It uses some kind of masking, and it's self-supervised learning in order to learn how to extract relations. And this particular system, when it was tested on a benchmark, on a widely used relation extraction benchmark called TACRED, it achieved an F1 score of 72.7. The second system has originally been trained on not only on a relation extraction task, but on a textual entailment task, on natural language inference, as we call it. This task, in case you don't know, is the task of getting two sentences as input and determining whether the sentences express exactly the same meaning, or whether they're independent, they have neutral relation, or one entails the other. So what the creators of this model has done is that they reformulated the relation extraction task as an entailment task, and in that way they have taken advantage of the pre-trained textual entailment engine. This particular model achieved in the same benchmark, TACRED, an F1 score of 73.9. So what I want you to notice here is that the two models seem to have a very slight difference in performance, in F1 score. What we're going to see through the adversarial evaluation is that there are important qualitative differences in performance between these two systems that this particular evaluation hasn't been able to show. So for these two systems, we introduced three types of adversaries. The first adversary is negation. So we thought, what happens if the input sentence, instead of expressing a positive relation, expresses the negation of a relation? So for instance, instead of having a sentence like Panos works for Textkernel, we have the sentence Panos does not work for Textkernel. Will the system be able in that case to say that no, the relation between the employment relation between Panos and Textkernel does not really apply? Similarly, in the second adversary, we want to see what happens if the input sentences express a past, future, or other tense variation of the relation. So again, for instance, if we say Panos is going to work for Textkernel, or Panos used to work for Textkernel, in both cases, we don't really have the target relation in this text, right? It's not the same as what happens in the present simple. And the third adversary that we wanted to introduce was about modality. So what happens if the input sentence expresses not a declarative version of the relation, but rather some kind of uncertainty or intention or advice? So what happens, for example, if we say that Panos probably works for Textkernel, or Panos should really go and work for Textkernel, right? Again, in these two cases, in these three cases, the system should not really return a positive assessment of the relation. For these three adversaries, we generated an adversarial data set. How did we do that? First, we consider each TACRED relation, and we generated a, in quotes, simple set of sentences using the pattern subject, relation, object, and we using a verb phrase lexicalization of the relation. So the input was really simple. We had sentences like John works at Google, John is employed by Google. Very simple sentences, where of course we expect all systems to be really good, right? To have an F1 score of hopefully 100%. But then we applied linguistic transformation templates and rules in order to produce sentence variations for its adversary type. So for instance, as you can see in the table below, we introduce negation. So John does not work at Google. We introduce tense variations like John will work at Google, or John has been working at Google. And we introduced modality changes like John might be employed by Google. For all these cases, we either maintained the existence of relation, or we flipped it, right? So this is important. It is important that the perturbation the change, the variation that we apply, that we know whether the meaning remains the same or changes. Now, so we generate this data set, and then we applied it in both Look and ASCII transformer systems. And we measured again the F1 scores and different accuracy scores for each of these. What did we find? We found some very interesting things. First, regarding negation, we found that Look, the system that has been trained on Wikipedia for the relation extraction task, was for the majority of the cases unable to correctly classify negative relations. So, in 80% of the sentences that contained a relation negation, the Look thought that the relation was actually there. On the other hand, the ASCII transformer system managed to successfully classify all negative relations. In the case of tense variations, both systems were successful in all positive variations. Positive in the sense that positive means that the tense variation kept the existence of the relation. But both systems also were fooled by all negative tense variations. So when we change the tense into so that the relation does not anymore apply, both systems were quite bad into understanding this. In the case of Look, it actually failed in all of them, 100% of the cases, whereas ASCII transformers was a bit better and was fooled only by 80% of those cases. Also, in the case of modality variations, Look was really bad. It was fooled by all modality variations, whereas in the ASCII transformers was fooled only by 50%. So what you see here is a very different picture than what we saw in the previous slide, where I just mentioned the two F1 scores, right? So even though the two systems achieved an F1 score on the benchmark data set, that F1 scores that were really close to each other, here we can see that they have a totally different behavior in some particular adversaries, like negations and modality, right? So ASCII transformers was really good at detecting negations. So it's a safer system to deploy in a situation where we expect to have negative sentences as opposed Look. And the same applies for modality variation. It's actually a better system than Look. Of course, if we consider other systems, this might change, right? The important thing here is to notice and realize that this particular type of evaluation that we're discussing here is able to identify better fragility than the typical way we evaluate NLP systems and generally machine learning systems. So, to wrap it up, 3 takeaways from today's talk. The first thing is that state-of-the-art NLP models and systems can be more accurate and may seem to be beating the state-of-the-art in many benchmarks, but they can also be pretty fragile, which means that we need, as practitioners and as NLP practitioners, to measure fragility and robustness. The traditional train test split evaluation is a very important type of evaluation, and it's always, of course, to be performed, but it doesn't always detect fragility. It's not a methodology that allows to assess the robustness of an NLP system. So for that, we consider adversarial evaluation as a technique that can help assess the robustness of a system and reveal its weaknesses. Thank you very much for listening to me. I'm available for any questions that you might have. Thank you very much.